happy that Georgios also agreed to present. So Georgios Piliouras from the Singapore University of Technology and Design, who is also a co-organizer in the semester, and he's going to be speaking today and in the tomorrow morning sessions. And he's going to be giving a dynamical systems perspective to many of the questions that were asked and addressed by Kostas's and Eva's talk. He's going to be giving us, like how those connect with dynamical system theory and chaos theory, and it's going to be some new tools that we can use throughout the semester to address and tackle those problems. Thank you very much.
Thank you, Vassili. All right, everybody. Hello. Yeah, so today I will be talking to you about tools that lie on the intersection of dynamical systems and learning in games. And yeah, so the goal of these talks would be to create like a bunch of like formal bridges between, I would say, 4 different areas. Is this a little bit too loud? The 4 different areas, I would say, almost of mathematics. So I have these like 4 different keywords. Okay, chaos, anarchy, regret, and equilibration. Right? So by chaos, I just put like a keyword effectively to capture tools that lie under the area of topology of dynamical systems. So one of that would be actually chaos theory, like what do we mean formal by chaos, and when does this actually emerge in game theory, and how can we actually prove it, right? But also not just chaos, but things like different notions of recurrence. So for example, of course, we're all familiar with the notion of a fixed point, and even the notion, let's say, of a periodic orbit. That's probably tools that all of us have seen even from high school. But now there's other notions of recurrence, like Poincaré recurrence, which are actually very important, and in some sense, they're necessary to understand even the most simple questions of, let's say, how does gradient descent behave in rock, paper, scissors? Okay. The second word is anarchy. Then, of course, here we mean the work of Christos and Eva and all of these people about effectively loss of efficiency or efficiency characterizations in games under different notions of equilibrium, right? And Eva talked about this quite at a length yesterday. And the third, of course, word by regret, I mean online optimization, and online optimization from the perspective of a single optimizer. Again, this is, of course, there's been a lot of like very recent fundamental work in terms of like how can we create algorithms that have like very, very low regret in many, many games. And today we'll actually be expanding on these ideas using tools from dynamical systems. And finally, last but not least, different notions of equilibria. Okay. So of course we have these notions that we've seen many, many times over, at least we should, like Nash equilibria, correlate equilibria, cross-correlate equilibria, and so on and so forth. But now what I'll be asking, and what I'll be hope to show you, is that these notions can actually be can have very unexpected interpretation if you actually try to understand them from the perspective of dynamical systems. Okay. All right. So this is hopefully the structure of the 4 different hours that I'll be talking about. So the first 2 hours are today, the second 2 hours are tomorrow morning, and then here's the large scale structure. So actually, I will start not with going through some sort of like classical ideas of learning in games, but actually showing like a brand new result that actually solves no-regret learning in general games. So we've seen, let's say, Kostis talked about his very recent work, very important work on his polylog regret algorithms in general games, which of course followed upon Vassili's fundamental work a few years ago on optimistic techniques. And now here we'll be designing like a new algorithm using some ideas of dynamical systems. And the kicker, I mean, just not to keep you somehow waiting, is that like this is going to be the total regret in any arbitrary game for all time. Okay, so first of all, as you see, there's no dependence on time. Okay, so that's it. N is the number of players, V is the range of payoffs, so from 0 to V, and M is the number of actions. Okay, that's it. So this is going to be the total regret, and actually the proof would be very, very, very straightforward. I claim that I'll come like very, very close to actually giving you the full proof today, hopefully in 1 hour. Okay, so that's my goal for the first hour. And then I say like, okay, we solved no regret learning games. What's next? Well, actually, we have to go beyond regret. And then, so in my second hour, I will go over, questions about price of anarchy and relations about, issues in the robustness, smooth framework that has been very successfully developed over the last decade, roughly. And so how there are some interesting issues in there that ask for like interesting extensions. Okay, and these ideas, again, these issues will be really coupled with ideas from dynamical systems. And finally, as I said, like, but maybe I'll keep this for tomorrow, is that like we could see that how notions of, let's say, recurrence and chaos can actually emerge both in the behavior of zero-sum games, also and in the behavior of potential games. So so here's the more interesting thing like I can tell you right now is that like, okay, to understand formally the behavior of, let's say, continuous time multiplicative weight updates, even in the case of rock, paper, scissors, like you have to know what Poincaré recurrence is. And actually you have to know what a Hamiltonian is. And then I will give you this definition, and then I will show you how this can give you structure, much more richer structure to understand the orbits, and then pose some very interesting open questions. Okay, so there's all extra things that need to be done, but I'll just give you the vocabulary. You can actually understand the open questions and start working on this. And then on the last slide, okay, potential games are arguably the easiest class of games. Easiest in the sense of like, okay, we understand that learning generally works as a gradient-like system. There's a Lyapunov of the potential always decreasing converging to equilibria. Well, we'll actually understand like, okay, under what kind of conditions can, for example, the systems go through bifurcations and phase transitions and even have, let's say, chaos in the systems, okay? And some other interesting questions that are related to efficiency, right? So that's the overall structure of the tutorial. All right, so let's start. Let's start with something, okay. Let's start with something simple. Now I scared you to hell, you know? So now let's go back to like, okay, something that will feel very comfortable. Okay, let's just remember, all of us remember, let's get on the same page about what's no regret. No regret learning is like, okay, we understood an algorithm such that with hindsight, no single deviating action significantly outperforms the dynamic. So here's the notion of regret, the definition of regret. Okay, here's the total profit of my algorithm. Here's the total profit of the best fixed action with hindsight. Okay, this difference, well, we call regret because the higher it is, the more unhappy we are. And we want this to be growing sublinearly with time. Okay, as long as regret goes sublinear with time, we call these algorithms colloquially no regret. And, you know, going all the way back to seminal works by Blackwell and Hanan, we know how to do that. Okay, very simple algorithm, give you square root of t regret. Okay, and here's my, for those of you who really somehow like just barged in, here's my cartoon picture of like a no regret algorithm. All right, so here's your optimization setting. You wake up every day, you know, and you don't know the weather through the day, whether it will be sunny or whether it will be snowing or rainy, but you have to take an action. So either pick a sunscreen with you or pick an umbrella. If you make the correct prediction, in some sense you get payoff of 1, otherwise you get payoff of 0. And let's say, okay, suppose you use some type of algorithm and you made these actions. All right, now you made the correct prediction like 3 out of 4 times. So your total profit is 3. All right, so now we say like, okay, what if I always chose umbrella? Profit was 1. If I always chose sunscreen, profit was 1. Okay, so this difference, you know, how much I could have gotten out of the best fixed action, which is 3, minus what we actually did, which is 0 in this case. This is called the regret of the algorithm. Okay, and this is what we're trying to keep as low as possible. All right, and now, okay, so when, let's say in our classes, we teach about no regret algorithms, typically the the most helpful starting point is to talk about the follow the regularized leader. Right. So this is the prototypical algorithms that perform an exploration-exploitation trade-off. Okay. So each agent on every day I, it chooses a mixed strategy xi that maximizes this difference. Okay. So first of all, these algorithms keep a vector in their memory, a memory buffer that keeps the accumulative performance of all actions so far. Okay, let's say I'm playing rock, paper, scissors. I have one entry for rock, one entry for paper, one entry for scissors, you know, and I see like, okay, how much money would have gotten in the first 3 days if I always play rock, if I always play paper, if I always play scissor. Okay, so that's my vector here of total or cumulative payoffs. And now when I choose my mixed strategy in the next day, I'm just solving this simple optimization problem. Okay, so argmax of this effectively linear function minus this strictly or strongly convex regularizer. Okay, now if this regularizer term was not here, then the behavior of this algorithm is very unstable. So you're always going to choose with probability 1 the maximum entry of this matrix. Okay, so clearly we don't want to be so fidgety. So we add such a regularizer here, for example, like the negative entropy is such a regularizer, and this somehow like favors more mixed strategies, and also like stabilize the behavior of the dynamic. Okay, all right. So hopefully this is something that most of you have seen, but this is something that maybe some of you have not seen. Okay, and this would be an important somehow like tool going back and forth in our framework, is to say, okay, that you can actually consider these dynamics not just in discrete time, but in continuous time. And I will use just to distinguish between the two, when I talk about continuous time, I will use the word dynamics, whereas when I talk about discrete time, I will use the word algorithms. Okay. So now, yeah, otherwise, these two worlds are the same, right? So it's exactly somehow like the same idea. Okay, the questions are like, okay, does your clock run in discrete time steps, as of course it only happens in any computing system, or do you use a mathematical idealization where you take time to be continuous? Okay. All right, and then as I said, in the case where you use the negative entropy as the regularizer, you get arguably one of the most famous online learning algorithms, which I get to call multiplicative weight updates. But I mean, this algorithm has been rediscovered like at least half a dozen times. It exists under at least, you know, I mean, sometimes I go online and I look for keywords. So like how people talk about these algorithms, you know. So aggregating algorithm, exponentiate gradient, heads, weight the majority, boosting, we now, and so on and so forth. Okay, and another thing that's actually very important is that this algorithm is the discrete time version of this ODE. Okay, so if we go from, as I said, from discrete time to continuous time, so if I go to the integral of payoffs, then the solution of those equations is given by this dynamical system, which is arguably one of the most famous ODEs, let's say, in mathematical biology and evolutionary game theory. It's called the replicator dynamics. Okay, and just to convince you somehow like these two things are the same. All right, so here, if you unroll the inductive formula, you get the following thing. You get that the probability of choosing some action I at time t is what is proportional to, let's say, e to the eta of a summation of the utilities of action I over t. Okay, so sorry, eta. So eta, this is the learning rate, so e to the eta 1 plus epsilon. Okay, and I claim that this is like an easy exercise for you to verify that if you take xi to the t and this to be now proportional to e over the integral of uat dt, you can show that this formula actually satisfies the differential equation. Okay. So the only difference between the solution of this ODE and the solution of multiplicative weight updates is that, like here, okay, instead of taking the integral over time, you show like you take discrete time steps. So each time step has length exactly eta. Okay. So okay, hopefully this will be this is clear. Okay, and here's the one proof that I will give you that I actually expect you to remember. Okay, everything else, actually maybe for the next like 2 days, it's okay to forget. But this one you remember because it's really 2 lines. And within 2 lines, I will prove to you that Replicator, the continuous time version of multiplicative weight updates, actually has bounded regret in all games. Okay, of course. Okay, so let's try to do this together. All right, so this is the formula for Replicator. All right, so the first thing I do is I take this probability on the other side, okay, just divide with this, and I just take integrals on both sides. All right. Okay, so far so good. This high school math. Okay, now again, high school math, I compute the integral on the left-hand side. And if you look at this and you stare at this, this is really the derivative of ln of x of a of t, right? So derivative and the integral sort of like disappear, and I get the difference between these 2 ln values. All right, great. Okay, there's another thing to, of course, that's relatively trivial. Is okay, x is a probability distribution, so it's a number which is between 0 and 1. So this is something that is negative. So I can just remove it, and I'm going to get now an equality. The left-hand side will only get better. Okay, and I'm done. That's it. Okay. So why? All right, let me just convince you. Okay, what is this thing on the left-hand side? Well, let's look at the first term. The first term takes the total utility for playing action action alpha over time. So this is my, payoff for deviating to the fixed action alpha, right? And this is just the inner product. This is your expected payoff at any time t, right? And then expected. So this is your actual performance of your algorithm over time. So this integral on the right-hand side is just the total regret for not deviating to action A. And this is upper bound by a constant. Okay, and this is for all actions. And I'm done. Okay, 3 lines. Okay, of course, there's a catch, right? There's a catch, and the catch is like, so right here, continuous time, you're really cheating, right? So it's really somehow like a mathematical approximation. We really ideally, want to put this directly in our laptops, but we can't. Laptops only work in discrete time, and that's somehow like the real tragedy in a sense. Okay, like we have this very beautiful proof, but we cannot engineer it, at least not in a direct way. Okay, so but now we'll figure out a way to do it in an indirect way. Okay, so that's the main question that we'll be exploring is like, okay, can we actually prove this kind of like guarantees in an actual like honest to God algorithm that we can like implement in our computers and compute it very fast? And we want truly constant regret, as I said, for all games. And right, and actually for all but maybe the last slide of the talk, when I talk about games, I just talk normal form games. Okay, don't think about anything more complex. We just like the vanilla game theory. Okay, and as I said, we'll just provide such an algorithm. And the important somehow insight here is that we will develop an algorithm that actually has a constant regret in general games, and it will do it in some sense in the most counterintuitive way possible. We will actually use fixed step sizes. So whereas somehow like, like fixed step sizes are typically seen as an anathema for online optimization, it's like, okay, look, just find the correct like decreasing rate, and then that's somehow like the game that we're going to play. Like how do you make sure that like different error terms somehow like cancel each other out? Here we'll have like a totally different approach. In fact, as we'll show, the regret of our algorithm would be linearly decreasing with the step size. The higher the step size, the smaller the regret. Okay, so not only fixed step size is important, but large step size is important. Okay, all right. So yeah, and basically the idea here that we're going to be taking advantage of is that there's a key difference between online learning and online learning in games. Okay, so in online learning, which is here we actually study an open loop system, and by open loop I mean that look, the payoff stream comes from the environment, comes from nature. You know, remember the example where I'm going out, you know, I'm stepping out of my house, and it might be sunny or it might be raining. Okay, there's actually no way to predict that. You know, that's outside your control. Okay, but when you're doing online learning in games, that's no longer true. What you actually see, okay, is of course not exactly in your hands, but it's in your hands of other players who are also like playing the same game as you and also apply learning dynamics. Okay, so actually the future evolves as a function of the current state, right? And for example, even in all this like, you know, optimistic approaches, the key insight is that like, look, as long as your step size is small enough, your future cannot evolve too much. Tomorrow cannot be all that different from today. Okay. All right. So yeah. So this is the key idea, you know, the key concept and insight of the optimistic methodology is that like, well, exactly. If you're playing a game, you're no longer, in the case of online optimization, there are other things you can leverage, right? And the idea that the optimistic class of algorithms leverages is that, well, tomorrow, as I said, actually it makes this assumption that tomorrow will be identical to today. Okay, and then this results in a slight recency bias, which makes the sequence of payoffs slightly more stable. Okay, yeah. So as Kostis actually talked to us yesterday, that's for example, optimistic multiplicative weight updates. It's the standard multiplicative weight updates update, but the contributions of the last period are counted twice, right? So if I would go, here, it would be something like this: t minus 1 plus 2 ua of t, right? Right. So that's the recency bias that's being introduced, and amazingly, as Kostis talked about to us, like this simple tweak suffices to create an algorithm such that, well, with properly and carefully chosen decreasing step sizes, leads to polylog regret. Okay, in general games, all right? So that's really a really great idea, but there's also like a slight caveat here. The caveat is that the optimistic approach effectively equates predictability with stability. Okay, so the prediction about the state of the system in the next period is only correct, perfectly correct, that is, if no other of the other agents moves. Okay, if I am the only one who gets to move, then indeed everybody will, you know, tomorrow will be exactly the same. Okay, but of course everybody moves. That's the problem. So now there's actually a tension, like the stability and hence the predictability of the sequence decreases with the step size. Okay, the higher the step size, the more unpredictable. Okay, but actually I want large step size, because the larger the step size, the more I exploit, right? The more payoffs I'm getting because I'm moving in the right direction. Okay, and of course this idea about vanishing step sizes is not just an idea that's used in optimistic algorithms, but effectively in all previous state-of-the-art solutions. Okay, So the whole idea is to sort of like, okay, find the correct rate of decrease, just try to get the error as low as possible. Okay. Now in this approach, we say something different. We say that actually the system can be perfectly predictable with no error whatsoever, without stability at all. Okay. Agents can learn aggressively and still be able to predict the future. Okay. That's the concept here. And this is an idea that we call clairvoyance. All right. And before I go into the details about how the algorithm actually, what's the nature of the algorithm, let's look at its performance. So here we compare, okay, 3 different algorithms. We focus on a 4-player 10-strategy game, so something that's not too much of a toy. And we look at what I call the vanilla multiplicative weight updates. So what happens if you use the classical 1 over square root of t step size for the total regret? Here we do the second, the red graph is the optimistic method with this state-of-the-art step sizes. And here is the new algorithm. Okay. And as we see, like here, the important thing here is that like this, we get, let me explain a little bit like the figures. So like the solid line in the middle, so we take like a bunch of initial conditions, like 100 initial conditions, okay? And then we plot the mean regret for each of them over time, right? And then we actually also plot the range of the max and mean regret for these 100 initial conditions, okay? So some initial conditions are like, let's say, more harder than other ones, and then that's what you see, okay? Right. And then on the third panel, we see this new algorithm, and the black line is going to be the theoretical upper bound, and the green line is the actual performance. Okay. And what I want to point out here is that the step size here is eta is equal to 1. So here I'm already running multiplicative weight updates with base E, right? Right. So that's already pretty high. Okay. But what is really somehow remarkable is, okay, remember, this is the green line. Okay. Now I'm going to increase the step size. All right. Okay. So I'm going to go from eta to the 1 power to eta to the 2.579 to eta to the 5th. Okay. So eta to the 5th, that's like, it's more than 100 on the base of the exponent. Okay. And here you see the total upper bounds, theoretical upper bounds on regret. Okay. So you see here, the upper bound that we can actually prove is 4.61. That's for the total regret for all time. You could run this forever. The sum of the regrets will not get larger than 4.6. Okay. Whereas the other algorithms, even within a few thousand iterations, they're already in the 300s. Okay.
So,
Yes. Mm-hmm.
So you're comparing multiplicative updates in different algorithms. What feedback do you get from the environment?
I mean, we'll go into this.
Is it a fair comparison? In other words, or is it like you get much better knowledge? You have better knowledge of the utility function.
I mean, let's have this discussion. Like once I describe the algorithm. Okay.
Question from the
Yes.
online audience.
Mm-hmm.
Do you make any assumptions on the game? Is it a zero-sum game?
No.
So
The results, okay, the results hold for absolutely any normal form game.
that all players play the same algorithm? Like,
Correct, yes. All players play the same algorithm.
have you tried running optimistic multiplicative weights with theta equals 1 in the experimental setting?
So that's a good question. My sense, okay, we have not really run this, but I expect that experimentally it will do better. So actually, I think it's generally a good idea to use non-decreasing step sizes but you have to be a bit careful because without very careful theoretical arguments, it could be the case that somebody could construct the games which are rare, where you have like very where you could really get trapped somehow in some chaotic orbit and have high regret. Yes.
Just about this question, I think following the narrative of Kostis yesterday that says that actually optimistic or exaggerating is an approximation of the clairvoyance. What is the meaning of the clairvoyant optimism? With the meaning that we're trying to make the.
We'll see the definitions of the algorithm. So let's pause the discussion to get the technical part. Yeah.
Can you say anything about the regret? Actually, it seems like it decreases over time. Or sometimes it goes down.
Yeah, so that can actually happen, right? So you can have like, you can even have like negative regret, right? So that's definitely a possibility. Yeah. Any other questions?
Can I ask a clarification? So in the definition of regret, you're comparing with a fixed action, right?
Yes, correct.
But when you actually perform the fixed action, your opponent would also perform different strategies.
Yes.
Right. So basically when you change your strategy, the opponent also changes. So how do you make sure that?
So in the regret framework, like when you complete your regret, you look at the actual realization of play, and only you get to deviate.
Also,
yeah. So it's this counterfactual, right? You see how you behaved in the last year, and you say like, oh, let's say you're in the stock market, You say like the stock market, the prices evolve because everyone buys and sells, and then you say at the end of the year, it's like, what if I bought Google, Then you see how much money every day.
Can you hear me?
Yeah. All right. Let me use this in a minute. Oh, I think it's back. I think we're back online. Right, thanks. That's fast. Okay. So as I said, when you do this counterfactual test to compute your regret, only you get to deviate. Okay.
So this is a follow-up question. So then when you compare different algorithms, their opponent are also using different algorithms, right?
Yes.
So could it be that you achieve lower regret because you have a weaker opponent? Is that
so? The thing here is that like it's not. So in all of these settings, like in some sense, you just don't necessarily think your other algorithms as opponents. Everybody somehow like applies specific kind of optimization technique. Everyone is trying to like maximize something for themselves, right? And then you say like, okay, we're all in this together. Maybe the game is zero sum, in which case we're opponents. Maybe it's cooperative, in which case we're partners, right? But in all of these settings, you can always ask the question like, how is my regret, right?
so? Well, here's an extreme example, right? If every opponent just plays uniformly randomly, according to this measurement of regret, wouldn't you have a regret of 0? Because if everybody just plays uniformly random, you don't really benefit from debating.
Why not? I mean, okay, like maybe I won't expand too much on this. We can have this discussion maybe offline. But if this uniform strategy is not an as equilibrium, and everybody plays this again and again and again every day, then of course I have like a best response that will give me like something else much better. So actually your regret will be linear in this case. Okay. All right.
Georgo,
yes.
Can you say something about the experiment? So I know that so for zero sum, it's easy to show that the sum of the regrets should be always non-negative.
Right.
And I have seen negative regret in, for example, boys and beans type of games. So congestion type of. So your example, your experiment is on coordination games.
So this, okay, so this game is some type of coordination game. I don't remember the exact details.
Okay.
But yeah, but our upper bound should be constant for any game.
Sure. I was talking about the negative.
Yeah.
So it's you think it's coordination, right?
It is, yes, it is a coordination.
Yeah.
But it's some weird because it's a 4-player one. There's some weird coordination problem. Okay, cool. Okay, all right. So let's start it. Okay, so this is where the technical part of the talk actually starts. And okay, the paper is available online. This is joint work with Ryan Statis, student and postdoc at SUDD. Yeah, so everything, if you want to look at more details, you can do that. Feel free to do that. Okay, and as I said, the goal for the rest of the talk is to actually try to give you a relatively complete understanding of the proof. The proof is actually going to be very straightforward, I claim. Okay, so let's try to do this. If you have any questions, please feel free to stop. Please. Okay, so just a bunch of terminology, just to make sure I'm on the same side, same page. Okay, I have n number of players. Each player has selects players from a set of strategies Si. And here we understand that normal form game for the utility of every player is just a function from this product of strategies to the real numbers. Okay, and that's your payoff. And of course, I allow players to use mixed strategies, which are just points on the simplex, right? In which case, we have a profile of mixed strategies, so one mixed strategy for each agent, and the utility extends over mixed strategies in the usual way by linearity of expectation. And I will also use a little bit of extra notation. I will use this UI-SI notation to denote what is the utility of player I if he deviates to strategy SI given the mixed strategy profile X. Okay, so this is exactly, so it's the utility of player I when I play pure strategy SI and everybody else but me plays as in X, right? And then I will be able to concatenate all of this together and get a vector VI. So UIs are scalars, right? Is my expected utility for player I. VI is going to be the vector of all of my utilities. Let's say if I play rock, paper, scissors, it would be my expected utility for playing rock, for playing papers, and for playing scissors, right? Given the randomness of my opponent. Whereas a UI is like my current expected utility. Okay. All right. Are we okay on the same page about notation? All right. So just to give again a brief reminder, here's the formula for multiplicative weight updates. So here I use this formula with the eta in the exponent. Okay. So and this is the typical update rule. And once again, a reminder that this is nothing but the FTRL formula with entropic regularizer. And then here's what I told you about this vector VI. So VI is my vector of expected utilities. It's exactly what I need to feed into the Y vector to keep update the historical performance of all actions. And then I'm just doing the argmax step for follow the regularized leader. Okay. All right. And here's the version of optimistic multiplicative weight updates. Okay, so here the only difference between multiplicative weight updates and optimistic is what we plug in here. Instead of like plugging in exactly the utilities at time t, now it's 2 times the utility minus the utility on the previous day. Okay, and yes, and as we said, this comes from the assumption that we use the last observed behavior as the predictor. Okay, and yeah, so here's the new algorithm. Okay, so here's the clairvoyance. Okay, and clairvoyance is exactly multiplicative weight updates, well, with one small but very critical difference. Okay, when I compute my utilities for the different actions, right, I actually take in the probabilities of my opponents tomorrow. Okay. All right. So so this is again clearly somehow. So the important thing is that like the probabilities at d plus 1 are both on the left and on the right hand side of the equation. So these type of equations are called implicit. Okay. Now, of course, this is something that you cannot possibly do, let's say, in online optimization, because you have to be God. In optimization, you say like, okay, if you know what tomorrow is, like, you know, let's play together. Like, so let's go to the casino. Okay. But I claim here we'll be able to do it. Okay. But right now I'm just making these problems. I'm just writing some stuff down. Suppose I can do this magically. Okay. And then we will unroll the magic and we'll show how to actually do this. Right. So what is the key idea behind clairvoyant multiplicative weight updates? Okay. Is that like the system actually tries to form self-confirming beliefs about what all the other players will play at any given instance. Okay. Here's what I'm putting here on the left-hand side of my formula is what I believe everybody else will play tomorrow. Okay. So this is also like what Kostis does. This is also like what Mike does. Okay. So we all have these beliefs about what each of us will play tomorrow. But it turns out that these beliefs are consistent. Okay. When we apply our beliefs about each other, what gets realized is actually what we play tomorrow. Okay.
So, George, how is this different from mirror probes with regularization?
Oh, there's no
like, you know, implicit method with tropic regularization. Is this what comes out of solving that? Isn't that what comes out of solving that?
No, not necessarily. I mean, like, I don't see any immediate connection with proximal here in the general sense, especially when you put in boundaries. But let's pause this, because even if there's an alternative formulation, let's try to figure out, first of all, why this thing is well defined, right? Like, so why could you even have the hope that something like this could possibly be true? I mean, right now you should be thinking yourself and say like, oh, this is impossible. Okay. So I'm going to try to unroll it a little bit by bit, and try to convince you that this could be plausible. Okay. So what's the first stepping stone? Okay. So first of all, okay, I have to start with some type of beliefs about what the system state will be tomorrow. Okay. And I'm saying like, let's do optimism. The very first hypothesis that I'm going to do about what the state tomorrow will be is what happened today. Okay. But now I'm going to plug these things here as my guess. Okay, this is my guess, my 0th guess. And this will give me some update. Okay, this will give me from 0 to 1. This will give me a new guess. And I'm going to say like, okay, check these two vectors. If two vectors are the same, then I was extremely lucky and I immediately found myself on a fixed point. Well, if not, then I have a new guess. The counter here has become 1. Okay, just plug it in again. Okay, now I'm going to get step 2. Keep iterating, and cross your fingers and hope this actually fixates. Okay.
I'm confused. What do you know about your own utility and other people's utility? Do you know everybody's utilities?
So here the system here, each player in the update room only needs to know their own utility.
But how do they understand everybody else's actions? Like after I do one update, everybody updates. So how do I know what update you made?
So this is, I mean, this is a code that's running in your laptop, right?
I understand, but do I need to know everybody's utilities? Is my question. Like the home function.
Who's you? Who's you?
I'm one of the players
Yeah.
who wants to run this fixed point equation.
Yeah.
So to make these updates, I need to know everybody's utilities, it seems.
So all you need
The
to
functions.
this can be communicated. So so you could, as long, let's say if we want to do it in a decentralized way, one way to do this is to say like, okay, look, everybody has seen what happened yesterday. and now we post our updated beliefs to like a common pool, okay, to a common block. Okay, everybody sees these updated beliefs, it just computes the next belief and so on and so forth.
Sure, but you don't pay regret for any of these updates. I mean, like,
Correct,
here's
yes.
another algorithm, right? So we all solve the equilibrium, right? And then we play like we solve for the equilibrium of the problem, and then we play those strategies forever. So in one round, we get zero regret.
True.
Okay.
But what we'll show about this type of update is like this converges linearly. Okay. So within, let's say, a constant number of iterations, a constant amount of overhead, you actually equilibrate. Okay. So instead of like running one, let's say, division, you have to run 32 max. And that's it. That's not a huge extra overhead, right? To get bounded regret. Okay. I mean, at least that's my interpretation. But all right, let's try to see first of all. Okay, and of course, there's an analog of clairvoyant FTRL, which is just exactly the same formula as the standard FTRL. But again, there's the trick that when you compute your utilities, you update your aggregate vector of utilities, you use tomorrow's utilities, right? Not today's utilities. Okay. And in the next slide, I'll actually show universal upper bound on regret for all regularizers and step sizes, as long as you can implement this formula of clairvoyant FTRL. And actually, the idea is pretty straightforward. Okay, so here's the total bound, I'm saying. So clairvoyant FTRL has the following bounded regret in all games and for all ages. Okay. And here's effectively the proof sketch. I mean, the proof sketch is something that like actually most of us have probably taught when we teach online optimization, is that like a clairvoyant FTRL is effectively be the leader type of algorithm, right? Because I actually optimize while knowing what will happen tomorrow. Okay. So there's a standard, like relatively, there's a standard inductive kind of argument that says like all be the leader arguments actually have non-positive regret. Okay. So where's the regret coming from? Well, there's one extra day, right? So there's a fictitious costs that are coming from the very first day where you introduce the costs of the regularizer. Okay. And that's where the regret of the clairvoyant FTRL is coming from. Okay. It's only due to the regularizer costs, and then this leads to this upper bound on regret. Okay. So specifically for the case of clairvoyant multiplicative weight updates, it's ln to the number of actions divided by eta. Okay. All right. So now you say, okay, because this you say, okay, this is great. Like you gave me like constant regret. Modulo, I do something magic, like maybe compute mass equilibria in a single iteration. Okay, now I will use the rest of the talk to convince you that you don't need actually magic. Okay, you can do this efficiently. All right, so here's the problems that you should worry about in any actually implicit method. Okay, so first of all, is this, does this equation have actual solutions? Okay, this is not clearly not guaranteed. Okay, and then could you actually have like multiple solutions? That's actually maybe less of a problem, but having no solutions is a possibility and it's an important problem. Okay, so we saw two different results. Okay, first of all, for any eta, no matter how aggressive you are, take eta 2 to the number of atoms in the universe. Okay, this CMW algorithm is actually well defined. Okay, but Kostis here is right. So if I take eta to infinity, the fixed point problem that I'm actually trying to solve is formally an approximate mass equilibrium, and it's going to be PPD hard to solve this. Okay, but that's okay. I will show you a constant upper bound on the step size, and as long as your step size is below that, then the algorithm that I described, this map, is a contraction, and will converge. Actually, we'll find the unique solution linearly fast. Okay, and that's it. That's putting everything together. All right. So
to understand for large eta, it's the fixed points are naturally linear of the problem, but for small eta,
yes,
it's a contractive map and the fixed.
correct. And let's see actually why this is formally the case. So this is universal upper bound on the accumulative regret. So on the single day, this is captures how an approximate equilibrium you are. So it's PPAD for too large, PPAD hard for too large of an eta, but for constant, not too large, then it's can be computed linearly via contraction. Okay, I have 8 minutes. I have 8 minutes, so I will actually skip the existence fixed point proof, but I'll just say this. Effectively, this is a Brouwer fixed point proof. Okay, this is not be too surprising. Okay, there's a little bit of a technicalities. We actually use something that's equivalent to Brouwer fixed point, but this is more like of a stylistic choice than anything really important. But it's a fixed point proof. The thing that's actually more interesting is the algorithmic part. Okay, how do you prove that this is actually a contraction? All right. So here's the mapping. Okay, the mapping is so this takes now as a parameter a current location of an agent. Okay, and it takes as input the current utility vector. Okay, and the utility vector, of course, can be treated as a function of the space of mixed hierarchy profiles. Okay, and now I want to prove that this is a contraction. Okay, so I start with my initial guess. You know, everybody starts with a guess, and these guesses will converge to a unique fixed point. And to do that, we need to show that we need to establish a contraction. So we use the following notions of distance between these two distributions. So this is two mixed hierarchy profiles, x and x prime. Okay, and then we just take the max of the one norm of the differences. Actually, on archive we also have like a different proof for the two norm, but if you're interested, yeah. And then this is the map. Okay, so the map takes as a point the current mixed hierarchy profile. Okay, and then it outputs the next mixed hierarchy profile for everybody. Okay, and now what we say is like for these notions of distance between two distributions. Okay, if you look at the initial distance between the distributions and the distance between the update distributions, this is going to be upper. You know, this factor is going to be upper bounded by this, right? So clearly, if eta is less than 1 over v times n minus 1, then this is going to be strictly less than this, and then that will give you a contraction. Okay, so this is the thing that we want to prove. Okay, and then at that point will be done. Yes.
So one question. So if I know my utilities,
yes,
can I run one step of a function g, one iterate?
If I know my utilities, can I know?
I know the costs of the payoffs of my utilities, right?
Yes.
Can I run the whole system? Can run one iterate of g? Can I compute g of x t?
I mean, you need the vector of utilities, right?
I mean,
so g of x depends on everybody. G.
I know my utilities, right?
Yes. Yes.
Or should I know everybody's utilities? Should I know the game? That's my question. And then the other question is, should you account for? So you compute a fixed point, right, or an approximate? Maybe computing exact fixed point is not realistic, but should you account this in the regret?
Okay.
All
good
these
question.
items.
Good question. Good question.
Yeah, that's okay.
All right. So here, as I said before, so this map is a concatenation of different maps. Each map can be computed locally as long as you know the last hypothesis of the system. Okay. As long as you know that, and you only know locally your utility, you can compute your part of the update rule. Okay. So that's question number one. Question number two, and this is accurate. Okay, what we prove here is a contraction map, right? So it means that like we're going to get within computer accuracy of the correct solution, right, of this fixed point, okay? But you can raise the same somehow concern for any algorithm, like multiplicative weight updates or optimistic, right? When you compute, and when you take any division, you don't compute the division with infinite accuracy, right? There is some approximation. Okay, the approximation is like 2 to the minus 64. Okay, these things may add up, but they add up kind of like slowly. So I don't worry too much about them.
Back to the first question, how you can compute locally one iterate of the mapping if you know, I mean, you need to know your utility at least everywhere, right?
Yes,
so,
yes.
so you need to know
your utility
function. Your utility function.
Yes.
You need to know the function, right?
Yeah, I mean, you need to know what your payoff is.
No, it needs to be defined the whole product of simplices, correct? You need to know it.
I mean, you see what you need here, right?
Right.
Right. So you need your vector, given what everybody else is playing right now, you need to know your vector of expected utilities. My utility for playing rock, for playing clay, for playing scissors, given the randomness of your opponent. That's all you need. You don't need to know anything else, right? I mean, you need the same information that multiplicative weight update needs. You know, this is actually a multiplicative weight update step.
No, but you get some steps for free. I think it's like all these iterates are not counted as bad payoffs that you collect.
True. So all those payoffs you don't actually play. So one could actually say, okay, look, you guys, you need to amortize for that, and I think we're definitely willing to do that. But I said, like, I think this is not not a really such a steep cost to pay, because since this is a contraction map, you only pay a linear amount of computational overhead, and that's it. Right?
So even the 1/t lower bound of Costis, it's information theoretic. So you need to see the matrix. Somehow he has zeros everywhere in the matrix. He has one column which is non-zero. I mean, Costis can say, right? So information theoretically you can get the 1/t because you haven't seen the whole matrix yet. But you somehow, when you do these iterates, you reveal information about the game. That was what I was asking.
I think you
Sorry,
you
yeah,
asked,
but
I think I'm running out of time, but I'm more than willing to have this discussion like offline.
Sure.
I'm really close to being done. Okay. Sorry, I didn't finish. I was meaning to go through this. All I want to say is like, look, this is it. This is the proof. Okay. It's 5 lines. Okay. I promise to you that, like, if I have like a few extra minutes, I could actually go on one line after line and convince you that this is actually not anything too complex. But you have the slides which are available here in this tiny URL, and then please free to go through that. And then for more details, you can find the paper. Yeah. All right. Let's put everything together and wrap up. So what I'm claiming is that, like, okay, what we showed is that this map, as long as the step size is upper bounded by this quantity, so V is the maximal payoff from 0 to V, N is the number of agents. So as long as your step size is at most is large, then this map is a contraction and converges to unique fixed point at a linear rate. Okay. Now, if you put everything together, like, ln divided by the step size, you get this type of regret bound. And as I said, importantly, this holds for arbitrary normal form games. And actually, okay, so although I'm not going through this today, you can see that you can actually go well beyond normal form games effectively on the same proof. So the proof about the FTRL being bounded regret, it generalized to concave dependence of the utility on your own mixed strategy. Actually, the dependence on 2 minutes there. The dependence on everybody else just needs to be smooth. You don't need convex or concavity. Importantly, and almost surprisingly, you can actually deal with time-evolving games as long as, of course, you know what the game that you play tomorrow. So today I could be playing rock, paper, scissors. Tomorrow I could be playing like matching pennies or whatever. like as long as I have this oracle access to the game, I can do this. I can deal with regularizations and many other stuff. Okay, there's some things. Okay, this is a little bit joking aside, but like this is something that is important. Okay, so I claim that like we should be thinking about learning in games with these two different desiderata in mind. But first of all, like constant regret is possible. I mean, it's possible within 3 lines in continuous time. Now we know that it's possible in discrete time. Okay, so how close to 0 can we actually get? Okay, and second, which I think is important, but really not something who have not paid attention enough, like what about like large step sizes? Actually, it's really powerful to do to be able to adapt fast, right? And to still have control over how your system evolves, right? And possibly we can use clairvoyant ideas and different variants to try to push, both of these directions to their extremes, as we saw it, and we've been discussing with Kostis. We know that at some point PPAD hardness will come into play. Like otherwise, somehow, like the world will fall apart. Okay, but how close to 0 can we get? Okay, we don't know. Open question. And of course, and then this is what I said, like my one slide about everything else. So all of these results are effectively about normal form games, but okay, like everything else, open question. So yeah, have fun, and that's it. Thank you. Dave?
Make sure there's one non-Greek asking a question.
You're not Greek.
So I didn't understand. First of all, you said Brouwer's fixed point, but then you started talking about contractions. And you only need continuity for Brouwer's fixed point. So I didn't realize what. I guess maybe uniqueness is the key.
All right, great. Thanks. Let me go back to the proof and try to give a little bit extra time to actually show you the proof I didn't show you all. Okay. So okay. All right. So let's see. All right. So we have the fixed point. So I'm going to call the denominator ZI because that thing is going to disappear quickly. And I'm going to take logarithms on both sides. Okay. So now this is my equivalent reformulation of my fixed point problem. Okay. Now what I do is I choose one fixed strategy for one of the agents. Okay. So this is log of my probability of playing some strategy SI at time t+1 minus log for the probability of playing SI at t is minus my utility at time t+1 plus the regularizer. Okay. And by choosing some fixed strategy, the first strategy for each agent, and subtracting, I make all of the regularizers disappear and get this formula. Okay. So this is the thing that now I need to solve. Okay, are we together? Right. And now I'm going to do a sweet little change of variables. So instead of like working on the simplex, okay, sum of xi's is equal to 1, xi, actually the interior of the simplex, xi is positive. I'm going to use this transformation and say like, okay, just give me a point in R n minus 1. And how do we get these points? Just by this transformation. Okay. And then the reason why I like to do this is because now I get 2 real numbers here, one real number, another real number. This is unconstrained. This is a diffeomorphism between the interior of the simplex and the whole R to the n minus 1. Okay. So there's 1-to-1 everywhere. So the whole R to the n minus 1 is available for me. And then if you look at what happens, and there is this part, and this part is like, okay, this is a constant because this is fixed, something that happened at time t. This is not part of the fixed point computation. This is the difference between these two utilities. So let's say the utilities between 0 and 1, this is also like bounded. So all of this quantity is bounded. Okay. So take this as something bounded, right? So now I'm saying like, look, I have something bounded, okay? I have something bounded, and here I have something that works in R. Okay, so if this number becomes small enough, then this is going to be negative, regardless what all the other variables are. Okay. In the other direction, if this becomes large enough, then this quantity will become everywhere positive, no matter what the other variables are doing. Okay. So the fact that such a systems, so this is, you need some generalization of the intermediate value theorem. So if you only had 1 degree of freedom, the fact that you have the 0 is the intermediate value theorem. Something that's continuous, here it's positive, here it's negative, there's a 0. Now you have a sequence of functions n with n controlling variables, but you have some boundaries, and in these boundaries you have a well-defined sign. So now they have a common 0, and that's it. And yeah, goes back to Poincaré. We'll be seeing a lot of him today. Yeah.
I think we should take questions of mine.
Okay. Okay. Yeah. Sorry. Thanks. Thanks.